السلام عليكم. السلام عليكم.
دكتور محمد، ازاي حضرتك؟
طبعا خير، ازي حضرتك يا دكتور خالد؟
ازيك يا فندم؟ ازي حضرتك؟
الله
نبدأ يا
يخليك.
دكتور ان شاء الله.
طيب تمام.
بريزنت البرزنتيشن يا شباب. هتشيل البرزنتيشن يا دكتور؟
هشير حالا البرزنتيشن، حاضر. انا بس محتاج ان حضرتك تسمح لي اعمل شير.
ايش؟ تشيك شيلت يا دكتور، شيلت.
حاضر. حضرتك شايف الشاشة دلوقتي؟
لسه. انا شايف الشاشة يا دكتور، شغل البرزنتيشن بقى. ايوه تمام.
طب تحب حضرتك نستنى شوية ولا نبدأ على طول؟
لا، نبدأ على طول يا دكتور، الساعة 9 يعني،
طيب.
عشان السيشن طويل.
طيب انا صوتي مسموع كده يا دكتور؟
ايوه يا فندم.
طيب. بسم الله الرحمن الرحيم. In the beginning, I'd like to thank the committee chair and the audience for paying attention to our work, which is entitled Self-Free Influential Nodes Detection in Mobile Social Network. The work actually is in the frame of a thesis of one of our students in Ain Shams. She couldn't attend for some reason. So I'm Muhammad Al-Alimi, Muhammad Hamdi, and I'm presenting the work today for the session. In the beginning, um, the mobile ad hoc network is a kind of wireless network where the mobile nodes are free to move everywhere without no support of any centralized administration. The infrastructure they may use to achieve the communication is the Wi-Fi. For instance, in our work is Wi-Fi. Maybe other technologies like Bluetooth or Zigbee or whatever basic communication technology can achieve the network. On top of this network, the mobile social networks are a kind of social network that run on top of minutes. And this way, the users are capable to directly send messages to other users. They can easily comment or share contents without any central administration like in Twitter or X or Facebook or these applications. So they can directly communicate and use all the functionalities of the social networks, but on top of the managed technology. Here come the next layer of finding the influential users in the network. So who is the influencers? So if you can find the influencers or the influential users, you can easily disseminate data better than trying to start from less influence nodes. On the other hand, we may have these kind of selfish nodes. These selfish nodes, they receive just the updates from the network, but they don't reproduce the reactions to the network. So they supposed to let the information pass to the others, since the information dissemination is depending on collaboration between the users. We are in MANET. So if there is a selfish node that selectively disseminate the data, of course, this affects the performance. This paper proposes a selfish-free influential node detection protocol. So our target is to detect the influential nodes using the throughput or the data dissemination. So the hypothesis here is that nodes that disseminate more information are most likely the influential user. But the challenging thing here is how to do this in the presence of the selfish activities of some users. So our motivation is identifying influential nodes to improve the data transmission. The selfish behavior affect efficiency of any communication mean. It's obvious now. The proposed model mitigates selfish effects. So we assume that selfish nodes are there, but we'll try to minimize the effects of these selfish activities. And we highlight here in very brief form the various approaches that exist in the literature are always for detecting the influential nodes, but they ever do this without the assumption of presence of selfish nodes. So the novelty of our work is detection of the influential node with the presence of the selfish activities. The proposed protocol, which is the selfish-free influential nodes detection protocol, identify the influential node and in a selfish network, it uses random walk for mobility and propagation of the network. So random walk here will play two important roles. The first one is a synthetic mobility model in our next simulation, as we are going to see. And the second role is using the same idea to probe the surrounding neighbors if there is any selfish activity. And we employ the DB-scan for clustering the user. So density plays important role to identify clusters of users that communicate on an interesting topic from their perspective. So our algorithm is locally on a distributed way, finding the influential or avoiding the effect of the selfish nodes and finding the influential nodes inside the clusters, which are formed based on the DB-scan algorithm. Actually, you can imagine that we have 4 layers interacting together to let our proposed work, a proposed protocol work. The mobility itself, where we employ the random walk mobility, so mobility of nodes in the MANET, then the social relations. Not all of the nodes are in a social relation. Not all of them are following the same influencer, or not all of them are friends to others, and so on. And then we cluster the based on these social relations, we cluster our nodes into different groups using the DB-scan. And then we let our algorithm to define the selfish activities and finding the influential nodes, however, presence of these selfish activities. Our main components are the network clustering, the random walk counter, and spanning tree. Then we let the users inside the clusters elect the influencers they follow or they get the influence from, or the origin of the influence propagation inside these clusters. Then we compute the data transmission, which reflects the influential node. The coordination, we can imagine our protocol, since it's actually not just an algorithm, it's a protocol, since we have the collaboration of the participant nodes takes an important role in the detection process. So it's a kind of coordination rather than being just one algorithm. In this coordination, we'll find the different components, these different components. So we have the clustering, and it plays an important role to shape the local clusters or the interesting groups, where the influence plays a role. And we build a spanning tree from each node to any other node in this cluster. To know the centrality, we are going to present the meaning of centrality. We have the random walk-based probing message. So it's while the nodes are moving, they send periodically message to the maximum spanning they can reach, and then later watch how are the selfish activities in this local hood affect their transmission. Then they share the counters to elect the influential nodes, and they can easily now have an idea where are the selfish nodes, and they can avoid sending a message to them. And then finally, from this local hood or local neighborhood, they can disseminate to the larger neighborhood the information about the influential nodes they see. To evaluate our protocol, we propose a simulation where we assume we have a network area of 1,000 square meters. The mobility model applied there is random random walk mobility model. The simulation duration is 10 hours. Number of runs are 10. The random walk probing length is 10 hops. So each node can probe to the 10 next hops. If there are 10 hops in the cluster, so the spanning tree levels are at most 10 hops. The message frequency is 10 seconds. Each 10 seconds, we send the random walk probes. We applied, as we already introduced, the DB-scan. We avoided the outlier nodes or the densities or the clusters with low densities. We exclude them from our computation. And the number of nodes working in this area was 3,300 nodes. We have two references in our evaluation, the selfish ignorant, or what we call SI, and the selfish considerate model, or SC. So these are the two references that we evaluate our configuration of the algorithm to. The SI, we don't assume that there is any selfish nodes. However, they are there, but we simply doesn't know that any of the participants are selfish. On the other hand, we are aware that, sorry. On the other hand, there is awareness about presence of these selfish nodes. Our experiments showed that higher mobility reduced dissemination efficiency, and this is trivial result. Lower mobility let the clusters be more stable and improve data dissemination. Regarding our perspectives of the selfish considerant and selfish ignorant, we observed 30% more efficiency for the SC surface on the account of selfish ignorant. The impact of the walk length, hops, the number of hops that you allow your probe messages to travel to. If you increase the number of hops to 12, of course, you can get better results. But at most, our protocol preserves 80% efficiency of detection and data dissemination in the lower number of walk lengths. Higher selfish nodes decrease dissemination, and this is trivial. But our protocol can preserve a better performance even if you have 50% of the participants selfish. So we are above 70%. Of course, the same thing in the data loss. The last thing, the centrality and the closeness. Centrality is how your node is in the center of the cluster. So it's the centralized nodes are better in dissemination than the outer nodes. Closeness, how each of these nodes are close to all of the network nodes. These actually are two metrics that we need to evaluate. So our need to categorize our detected influential node. So we already detected influential node in the experiments, how they are central and how they are close to the others. Again, the centrality is blue, and the closeness is orange. And against the mobility, as our mobility increases, the centrality decrease, and this is logic. And the closeness is still persistent. On the other metric, which is, independent parameter, which is the walk length, higher walk length guarantee both closeness and centrality. Closeness and centrality are affected by the selfish percent, but as we can see, higher selfish percentage lets the centrality collapse very quickly. Conclusions. Fully distributed protocol has been presented in this presentation. The use of random walk, DP scan clustering, and election mechanism showed possibility to achieve the data dissemination in the selfish environment up to 30% of the traditional model. Thank you, and back to the chair.
Thank you, Dr. Muhammad. Any question for the online audience? Dr. Muhammad Shitu, do you have a question?
Hello, good morning, sir.
Okay. Thank you, Dr. Muhammad. Good
Thank you.
presentation. Thank you. Okay.
Thank you.
اتفضل يا دكتور اتفضل.
I have to leave for the other session.
Yes, and I know. I
Okay.
know you are very busy today. Okay.
Thank
okay.
you, Prof. Khaled.
Thank you,
Thank you.
Dr.
Salam alaikum.
عليكم السلام ورحمة الله وبركاته. Okay. The next one, classification of diabetes using ensemble and the individual machine learning algorithm. Dr. Helmi, Ahmed Eddin, Weedy, and Fedrin Yusfid exist. Dr. Helmi, Dr. Helmi Ahmed Eddin. Okay, next, review of artificial intelligence techniques for recognize Arabic sign language. تغريد الجربوي. وائل يفوز. Yes. Dr. Muhammad Shitu.
Hello, good morning.
What's Muhammad Shitu?
Hello. Hello, good morning.
What's your paper? What is anomaly detection?
No, I actually sent my paper, but they told me that I sent it on late.
Oh, good morning. Yes. Helmi, you can start. Okay, Dr. Muhammad. Now, Dr. Helmi, we provide your presentation. Okay.
Okay.
Okay, Dr. Muhammad. Can start now, Dr. Helmi عماد الدين. Okay, classification of diabetes using ensemble and individual machine learning algorithm. Okay. Thank you, Dr. Helmi. Any question, Doctor?
Thank you, Doctor.
What about overfitting for dysentery? How to resolve problem of overfitting? Thank you, Dr. Helmi. A good presentation. Good job. Thank you.
Okay. Okay.
Please, Dr. Muhammad Shita, Dr. Muhammad Shito, please mute. Please mute. Please mute.
Okay.
Shukran. Thanks. The next one, Doctor, can you attend? Dr. Shaheen? Dr. Tagreed?
Hello.
Dr. Who's? Yes, anomaly detection in industrial machine using machine learning and the deep learning techniques with vibration data for predictive maintenance. Okay, Doctor? Shaheen
Yeah.
Uzman. Okay. You can start now. You can share it. You can share
Yeah,
your
sure.
presentation.
Can you see my screen?
Stop sharing and reshare again. Doctor, you can share. Dr. Shaheen,
I already shared.
you can share now.
Can you see it now?
No.
Recording in progress.
Can I start now?
No, don't disappear. I call technician.
Recording in progress.
Can you hear now?
Yeah, sure.
Yes, sure.
It's okay now?
Give me a second, Stanley. Yeah, we can see it.
You can start now, Dr. Shaheen.
Okay.
You can
Assalamu
start.
alaikum.
Alaikum salam rahmatullah.
Good morning, everyone. Today I will be presenting our research on anomaly detection in industrial machinery using machine learning and deep learning techniques with vibration data for predictive maintenance. This work carried out by myself, Shainuzaman Sanim, along with my colleagues. Industrial machinery operates in harsh environment where any failure can result costly downtimes. Anomaly detection plays a vital role in predictive maintenance, which aims to identify potential issues before they lead to environment failures. Our research focuses on using machine learning and deep learning techniques to detect anomalies in machinery using vibration data. Vibration data is collected from machinery sensors to identify irregularity in the system's behavior, potentially signaling impeding failures. The main objective of our study was to explore how machine learning and deep learning techniques could applied to detect anomalies in machinery using 3-axis vibration data. We focused on three models: one class SVM, isolation forest, LSTM autoencoder. Our goal to evaluate and compare the performance of this model in identifying anomalies based on vibration data collected before and after schedule maintenance. Detecting anomalies in machinery before they cause failure is essential for predictive maintenance. Machine learning and deep learning models offer an automated solution for identifying these anomalies. Vibration data being rich in information can highlight abnormal behavior in machinery. Thus, early detection can reduce both downtime and repair cost, ensuring the machinery runs efficiently. And for this study, we used 3-axis vibration data collected from industrial machineries, both before and after scheduled maintenance. The data set included 70,000 observation for each axis across 40 samples. The data labeled as after maintenance represents the normal operating state of the machinery, while data collected before maintenance may contain both normal and anomalous behavior. Okay. One class SBM is preserved machine learning algorithm that creates a decision boundary based on normal data. It works by mapping the data to a higher dimensional space and finding hyperplane that separates the normal data from anomalies. In our case, the model achieved an impressive 99.5% accuracy in identifying anomalies, making it the top performer among the model we tested. Isolation forest model isolates anomalies by creating random partitions in the feature space. The anomalies being rare and different from normal data require few party, thus make them easier to isolate. While this model achieved 92.9% accuracy in anomaly detection, it performed slightly worse than one class SVM due to its sensitivity and proportion of anomalies in the data. The LSTM autoencoder is a deep learning model designed for sequential data. In our case, it used to analyze time series vibration data. The autoencoder learns to reconstruct normal data pattern. Any significant deviation from the reconstructed data is flagged as an anomaly. The model achieved 94.1% accuracy, which was quite promising, but it did not quite match one class SVM in terms of performance. And feature engineering, feature restriction was performed using diagnostic feature designer in MATLAB, focusing on key domain and frequency domain feature. The feature extracted from vibration data were crest vector, RMS, standard deviation, mean, in SNR, THD, etc. These features are crucial for identifying patterns in both normal and anomalous machine behavior. Okay, the full data set contained 70,642 vibration signals. We split the data set into 90% for training, sorry, and 10% for testing. The setup helped to evaluate models' ability to distinguish between normal and anomaly states effectively. In this slide, we monitored the training RMSC and training loss of LSTM autoencoder over 4,000 iterations. The RMSC started at 5.8113 and dropped to 0.3418, while the training loss decreases from 33.771 to 0.5846. This study reduction indicates that the model progressively learned normal machine behavior and improved its ability to reconstruct vibration signals accurately. Here we see the reconstruction performed of the autoencoder for both normal and anomalies data. The model reconstructed normal data accurately with minimal error. However, for anomalies data, particularly for features 10, 11, and 12, the reconstruction error was significantly higher, highlighting the model's effectiveness in identifying faults. And figure 8 compares the reconstruction error between pre-maintenance and post-maintenance data. Before maintenance, the mean error was 4.13, suggesting anomalies. After maintenance, the mean error dropped to 0.57, indicating that model correctly captured normal behavior. This difference in errors confirms the model's ability to distinguish between normal and anomalous condition. Figure 9 compares the reconstruction error between pre-maintenance and post-maintenance data. Before maintenance, the visualization reconstruction error, low construction error was normal data, anomalies data, higher errors flagged as anomalies. The confusion matrix helps visualize the true positive and false positive rates for each model. For instance, the one class SBM had an accuracy of 99.5% with a 0.5% false positive rate for anomalies, which indicates it accurately separated normal and abnormal data in most cases. Also, for forest model, higher false positive and false negative, and for ALSTM autoencoder, good accuracy with minimal false positives. The performance of the three model was evaluated as follows. One class as SBM ASIV 99.5% accuracy, isolation forest ASIV 92.9% accuracy, LSTM ASIV 94.1% accuracy. Here, one class SBM model outperformed the others by significant margin, making it the most effective model for anomaly detection in our study. The machine learning and deep learning techniques are highly effective for detecting anomalies in industrial machinery. One class SBM stood out as the most reliable model with accuracy 99.5%, making it an ideal choice for predictive maintenance system. The LSTM autoencoder and isolation forest also showed promise, but it slightly lower performance. This model can significantly enhance the reliability and efficiency of maintenance system by identifying issue before equipment failures occurs. These are some key differences of our study. Thank you.
Thank you, Doctor. Any question? Okay, Doctor, good presentation. Uh, what about overfitting in your paper? Dr. Shaheen, I have one question. Doctor,
Hello.
your experiment must has overfitting. Do you hear me? Okay, doctor. Okay, thanks. شكرا. Last one, review of artificial intelligence techniques for recognition Arabic sign language. تغريد دكتور تغريد. دكتور تغريد. دكتور تغريد، دكتور وائل يفوز. Anybody else? Thank you. Okay. Yeah, for sorry, I must to finalize this session. Anybody exist? Dr. Tagrid? Dr. Wael Yafuz? Dr. Wael Yafuz? Dr. Tagrid? Yes, I have to finalize the session. Thank you.
السلام عليكم.
عليكم السلام ورحمة الله. دكتور تغريد؟
أيوة، لو سمحت معلش بس صارت عندي مشكلة في الإنترنت وتأخر علي الوقت.
خلاص اوكي مفيش مشكلة. No problem. Yes, you can start now.
أوكي، كيف أقدر أسوي شير؟
Okay, 1 minute.
Yes, doctor, can you share it now?
تغريد.
Yes.
Yeah, can you share it?
Yes, yeah.
Still not share from your side.
Dr. Tagreed, you can start now.
Okay.
Is there problem?
تمام الآن واضح.
Yes, okay. Yeah, yes, good. You can start now. Thank you.
Okay. Hello, my name is Tagreed. Hello, my name is Tagreed from Taiba University. I will talk about review paper in artificial intelligence technique for recognize Arabic sign language. My agenda: an introduction, problem statement, and research objective. AI technique for sign language recognition that include machine learning, deep learning, hybrid model. The challenge, well, conclusion, and future trend, well, limitation, and the future work. Why is my research paper is important? Sign language is a primary communication method for individuals with hearing impairment. AI has significantly improved sign language recognition. Our goal is to explore the last AI technique in this field. A problem statement and research objective. Recognizing Arabic Sign Language is difficult due to gestures, variations, and limited label dataset. Traditional method struggle with accuracy and real-time recognition. The objective: explore modern AI technique for Arabic Sign Language recognition, compare machine learning and deep learning model, identify the future research direction. The AI technique that in this paper include machine learning, deep learning, that include convolution neural network with transfer learning, vision transformer, and the hybrid model. The first one, machine learning. Machine learning required manual feature extraction from image and video, work well with small data, but struggle with complex data. Example in the support vector machine will key nearest neighbor and random forest. This table shows some study that use machine learning to deal with sign language recognition. As you see, KNN and LMB achieve high accuracy, more than 99, which show the effectiveness for machine learning in some cases. And the support vector machine has less accuracy, 83, which indicates that some algorithm need more data or better processing. Machine learning first challenge difficulty to deal with the huge data and need to extract feature extraction. In this figure show the difference between machine learning and deep learning. And machine learning required manual feature extraction by engineer based on domain knowledge, and deep learning automatically extracted feature from the data using deep neural network with small human intervention. Deep learning is better because no need to manual feature extraction and can deal with huge data and complex data. The first one in deep learning, a convolution neural network that designed for processing and analyzing image or visual data. And CNN have many layers, a convolution layer that extract feature like age and shape, and the Bolling layer reduce the data size while perceiving important feature, and the fully connected layer make the final decision. Table show the study that used CNN network. As we can see, the size of the data is much larger than in machine learning and achieve high results. A CNN network achieved the accuracy more than 97 in some study. The second model in deep learning, transfer learning, that work while knowledge gained from pre-trained model in one task and applied to another task, similar task. CNN work by train the model on large data set. An initial layer of this model is pre-training and used for new task, and the last layer of the model are fine-tuning to fit the new task. A transfer learning saves time and resource, can use it for tasks with limited data, achieve good performance even with a small data set. The table shows some study that use it in transfer learning. The accuracy range between 91 and 100. Using advanced model like ResNet or EfficientNet B4. The last model in deep learning, Alphagen Transformer. Alphagen Transformer used transfer architecture, originally the design for natural language process, but applied to image. Alphagen Transformer uses self-attention mechanism for better pattern recognition. How it works, the image is divided into small batch inside using configuration. Instead of using configuration layer like a CNN, this batch are converted into mathematical representation and passed through transformer encoder for image analysis, and the final decision is made by based on the information extracted by the transformer. Alphagen Transformer achieve strong performance in image processing. The study have showed that it can achieve higher result more than a CNN, but need to be trained in very large data set. As you see in the table, some study achieve more than 99 using Alphagen Transformer. The last model, hybrid model. Hybrid model combine different technique or multiple model to achieve better performance on specific task. A hybrid model use advance of each method to improve performance, achieve high accuracy in complex task, can handle with multiple type of the data. As you see in the table, the one study combine Alphagen Transformer with the CNN, and the second combine Alphagen Transformer with the transfer learning and achieve high accuracy. The challenge limited label data set for Arabic Sign Language. A real time implementation remain difficult. A high computation cost for Alphagen Transformer and Gaussian formulation increase complexity. A conclusion: a deep learning has a deep learning is outperformed than traditional machine learning. Transfer learning and Alphagen Transformer improve recognition accuracy. Look of the data is still significant problem in Arabic Sign Language, while hybrid model may be the best solution in the future. A future direction, expanding an Arabic Sign Language dataset, improve a real-time application for mobile device, developing more difficult hybrid model. A limitation and the future work. A limitation in my paper focus on foundation concept and the previous study without deep technical analysis. In future work, we aim to support the research with technical comparison between the model. Thank you for listening.
دكتور تغريد.
أيوة، تفضل.
Yes, okay. Any question? Okay, I have one question for your survey. Your survey on artificial intelligence techniques for recognized Arabic Sign Language only, okay?
Yes.
Yes. Okay, but you mentioned about some techniques in deep learning and neural network, but don't mention any issues about optimizer, like Adam optimizer or comparison between optimizer used in CNN. Okay.
Yes.
Okay.
In future work, I will add this, inshallah.
Inshallah. Okay, it is very important comparison because optimizer is a core of any techniques in CNN or in neural network. Okay, thank you, doctor. Good job, good work.
Thank you.
Thank you. Okay. Assalamu alaikum. Okay, let's go. We have to finalize this session. Thanks.